Hello everybody, and welcome to another video on my channel. Today is the first video of integral calculus. Basically, we're moving on to the other half of calculus after a long time studying derivatives and their applications. So, without further ado, let's begin. Today's video is about Riemann sums, or approximating area under the curves. Now, integrals is finding out the area under a curve, and the Riemann sums are actually the foundation for how that works, but that will be explained in a future video. Now, this is not all there is for Riemann sums. There are three major types of Riemann sums: ones that use rectangles, ones that use trapezoids, and one that uses quadratics. There are more, but they're often much rarer and normally take a bit more work. So, we're going to be sticking to those three, and then in the fourth video covering Riemann sums, I'll show how they really relate to integrals. I'll also show it in this video, but I won't be really covering it in that much detail as I will in my fourth video. So stay tuned for that, but for now, enjoy this one. This is the core idea. First, we break the region into rectangles. Then we calculate the area of each of these rectangles. We sum all the rectangle areas to get our approximation, and the more rectangles we have, the better approximation it will be. Setting up the problem goes like this. First of all, we have a given, a function f of x on an interval a to b. Number 2, we have the goal, approximate the area under the curve. Number 3, we have our method, divide the interval into n subintervals. Then we have the width of each rectangle, where we have delta x is equal to b minus a over n, where n is the number of subintervals that we choose or the problem chooses. There are three major types of Riemann sums. Now these are just general Riemann sums and are not actually specific to any of the three major types. First is a left Riemann sum, where we take the function from our left endpoint. Then it's the right one, where we do it from the right endpoint of the subinterval. And then it's the midpoint, where we take it from the midpoint. Now I have rectangle height because in this video we're covering rectangles. Here we have height determined by fx of the number at left endpoint of each interval. So x0, x1, x2, and then all the way to fx minus 1. And that's going to be the height of our function, and then delta x in fact will be our width. So that's how we calculate the area of the rectangles, by multiplying delta x by all of these. The right hand Riemann sum is the exact same thing, except it starts at the end of the first subinterval and goes up all the way until the final value, but we still have the delta x multiplied by the function. This normally, which we'll talk about later, tends to overestimate when increasing and underestimate when decreasing the area, and it's the exact opposite with left-hand Riemann sums. The final type of Riemann sum that we have is the midpoint Riemann sum. So, we have the midpoint of each subinterval. So if we have xi and xi plus 1, the midpoint is xi plus xi plus 1 divided by 2, and it shows over here where we have m over here, but in fact we could do like 0.5 or 1.5, but m just shows that there's a midpoint. Now often this gives better approximations than left or right hand sums, since they don't tend to overestimate or underestimate as much. So here is our first example, and the setup is shown over here. Now what we're going to do is, instead of just doing the function multiplying by each other, I'm also going to show you a graphical approach, and then we're also going to do the function multiplying in the same problem, because I think it's very beneficial for you to see that. Over here we have our graph, and I'm using decimals for this. So what's going to happen is we're going to have y is equal to x, and let's make this a light blue. After that, what we're going to do is, since it's the left-hand Riemann sum and everything is in 0.5s, what we're going to do is we're going to take the left-hand interval of each of those 0.5s. And wherever that x value is, we figure out the y value, and that's going to be the height of our rectangle. Now, since the left-hand end point from 0 to 0.5 is 0, there's not going to be any shape there. But from 0.5 to 1, the left-hand endpoint will be 0.5. So let me quickly finish drawing that rectangle, or in this case, it's going to be a square for the interval 0.5 to 1. Okay, over here we've drawn our first rectangle where the height is 0.5. Since when x is equal to 0.5, that's where y is. And we drew the rectangle over here, in which this case, it's a square. Now for our next interval, 1 to 1.5, the height, since we're taking the left endpoint, the height is going to be equal to 1. So the height is going to be equal to 1. So we're going to have a rectangle from 1 to 1.5 with a height of 1. So let me draw that really quick. Okay, over here we drew our second rectangle, and the same process is going to apply to the third, where we're going to have the rectangle with height of 1.5 since y is equal to x. So if the left end point is x is equal to 1.5, then what's going to happen is y is going to be equal to 1.5. So we did the same thing for the final area. Now what's going to happen is, now that we have all the areas, we figure out the areas and we add it up. Over here, since it's a square with side 0.5, it's going to be 0.25 is the area for this one. Now since it's 0.5 and 1 for the middle rectangle, that's going to be 0.5, and since it's going to be 0.5 and 1.5 over here, it's going to be 0.75. So overall, what's gonna happen is it's gonna be equal to 1.5, which compared to the actual area is a good amount less. Now you understand the drill mostly, so I'm just gonna tweak a few numbers, and we're gonna figure out the area for the right-hand Riemann sum. So over here we have the right-hand Riemann sum. And as you can already see, it's going to overestimate the area as there's so much outside the actual given boundary. Now that we have the graph, we can redo the areas. So 0.5 times 0, this square or rectangle will be 0.25, this will be 0.5, this will be 0.75, and this will be 1. So after adding all of this up, 0.25 plus 0.75 over here, that's 1, then plus 0.5 is 1.5, then plus 1 is 2.5. This actually overestimates the area that's within this shape over here, which is actually a triangle. So now that we have the right hand and the left hand, which overestimate and underestimate respectively, we can figure out the midpoint one. Now the midpoint one is where we take the midpoint of both of them and we use that in our rectangle. What's gonna happen is over here it's gonna have and so on until we finish for all of this, and I'll check in on you when that happens. So over here we have everything taken at the midpoint. And already, in fact, it looks like it's going to be closer because there's some areas that are omitted, but there's some extra areas. So let's add everything up and see how it goes. So 0.5 multiplied by 0.25 is 0.125. 0.75 multiplied by 0.5 is 0.375. So that adds up to 0.5, these two rectangles. So then 1.25 multiplied by 0.5 is 0.625, and 1.75 multiplied by 0.5 is equal to 0.875. So since we have 0.5 over here, and then 0.875 plus 0.625 is 1.5, what we'll get is that the total area determined by this. Now if we actually take the area under the curve, where over here we have a bunch of stuff. Over here we have the triangle pretty much. The area is actually going to be equal to 2. So the midpoint formula has it spot on and is far closer to any of the other ones that we covered there. That's example 1. And now let's move on to example 2. Example 2 is where we have x squared, interval from 0 to 3. The number of rectangles is n is equal to 6, and the width of each rectangle is delta x is equal to 3 minus 0 divided by 6, which is 0.5. So what we're going to do this time is we're going to use the function calculations. I wouldn't say cheating our way instead of using geometry or any other methods. We're just going to go ahead all in on the functions practice. That's pretty much what we're going to do, and let's start. So let's start by calculating the left-hand Riemann sum. Now, since everything is on an interval of 0.5, the width of each rectangle, we're gonna have 0. Now multiplied by, the first thing that we're gonna do is, since it's a left hand, from 0 to 0.5, we're gonna have x is equal to 0, so y is also gonna be equal to 0. For the next one, we're gonna have 0.5, so y is gonna be 0.25. Then from 0.5 to 1, we're gonna have, from 1 to 1.5, we're gonna have the leftmost one, so 1 squared is 1. Then from 1.5 to 2, we're also gonna have the leftmost one, so 2.25. Plus, what's gonna happen is 2 to 2.5, we're gonna have 2, so plus 4. Then from 2.5 to 3, we'll have 2.5 squared, which is 6.25. So what happens is this 0.5 plus 2.25 is 2.5, plus 6.25 is 8.75. So 0.5 multiplied by 8.75 plus 5, or 13.75. So 0.5 multiplied by 13.75 is equal to 6.875. So this is our answer for the left-hand Riemann sum. The next thing we're going to do is we're going to have the right-hand Riemann sum. So we're going to have 0.5 multiplied by 0.25 plus 1 plus 2.25 plus 4 plus 6.25. And then for the final one, since the rightmost endpoint is 3, we'll have plus 9. Now this, we're going to have 8.75 again, plus 5, 13.75. But then we're going to add that by 9. So 0.5 multiplied by 22.75. Now this is equal to 11.375. Now our midpoint is going to be a bit different. The in between 0 and 0.25 is going to be 0.25. So what's going to happen is, and that's going to be 0.0625. Then again, we're going to have plus. Between 0.5 and 1, we're going to have 0.75. And 0.75 squared is 0.5625. Then between 1 and 1.5, we're going to have 1.25 squared, which is 1.5625. After 1.25 squared, we're going to have in between 1.5 and 2, which is 1.75 squared, which is 3.0625. Then after we have in between 1 and that, so we have that's in between 1.5 and 2. So in between 2 and 2.5, we're going to have 2.25, whose square is 5.0625. And then in between 2.5 and 3, we're going to have 2.7, whose square is 7.5625. Now, if we add all of this together and multiply by 0.5, this result is going to be 8.9375, which in fact is a way closer result than either of the two. Using calculus, in fact, gives you the area of 9, so So the midpoint is only off by 0.0625, which is actually pretty good for only 6 rectangles. If we start increasing the number, it's gonna get way and way more accurate. Over here, I have everything copied down, but I honestly do think it's very surprising that only with rectangles we can get this far. Trapezoids normally take a little more work, but are often more accurate. Same with the quadratic method, which pretty much exactly estimates areas for quadratic functions. So here are a few observations. So, for increasing functions, the left Riemann sum is less than the actual area, which is less than the right Riemann sum. In the midpoint is always going to be pretty close to the actual Riemann sum, actual area, as long as you use enough rectangles. So it's not just one rectangle, because then it's not very accurate all the time. Next, we have decreasing functions, where its right is less than the actual area is less than left. Then always pretty much midpoint sum is more accurate than the left hand Riemann sum or the right hand Riemann sum. More rectangles equals a better approximation, and as n approaches infinity, the Riemann sum becomes the exact area. Now when we take the limit, the sum becomes a definite integral and it gives the exact area. So this is the foundation of what integral calculus is based on, and as I said, we'll discuss about this more in my 4th video about Riemann sums, which is gonna come in a few weeks. And thank you so much for watching. I'm really happy that you made it to the end, and if you found this good, educational, and entertaining, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And please make sure to comment down below any suggestions, tips, or tricks you have for the channel, because it really helps a lot. So thank you so much, see you in the next one, and bye bye.